Hello everyone, my name is Lorenzo Saino, I'm a software engineer at Fastly, and welcome to the Hashicorp London User Group. We have lined up today two very interesting talks. I'm really excited. The first talk is by Mack at OpenCredo, who's going to tell us a bit how to use Vault to harden a bit our infrastructure. And the second longer talk is by Armon Dadgar from Hashicorp, which is going to give us another talk about Vault. So before I leave the word to them, I would like to just basically give you a couple of words, describe a bit what we do at Fastly, who we are. And so we, Fastly, are a content delivery network. So any of you know what a content delivery network does? Familiar? Good. So a content delivery network basically is a infrastructure, a globally distributed infrastructure. We operate a number of POPs distributed over the world, and we use our POPs to distribute content on behalf of our customers to their end users. So by having our infrastructure globally distributed across the world, we allow the end users of our customer to have a much lower latency and much better performance. So from a conceptual point of view, basically we sit in the middle between our customers, which operate content, and their end users. Basically, whenever one of their end users want to retrieve a content, they first hit one of our POPs, and our POPs, we perform a number of processing. We can cache content on behalf of our customers. We can provide some dynamic site acceleration by tweaking a bit the TCP stack. We can terminate the TCP connection for them, terminate TLS connection, and also protect customers against the DDoS attacks. Probably you may have not heard about Fastly before, but I'm pretty sure that your browser has. So we serve traffic from a large number of our customers, spanning different industries. We got customers from media, customers from government services, from e-commerce, and social networks. So what's special about Fastly? Well, that's what we can do for you. We can improve your performance. We can serve content closer to your end user. And therefore, your end user can have a lower latency and a better performance. We can provide security for you because we can protect you against DDoS attacks. So if a DDoS attacks will take the hit, not you, we'll save your origins. Also, by providing you caching, we can reduce the number of hits that your backends receive. So we can actually serve traffic from our caches and therefore reduce the load at your origin and reduce your total cost of ownership. But what I actually really think that is the special sauce of Fastly is visibility and control. We give you, I think, unprecedented visibility and control in the way we handle your traffic and we serve your content. The thing is that the reason actually the Fastly was created was to overcome some limitation of our legacy CDNs. So legacy CDNs normally don't give you a real-time understanding of what's happening in our caches. You can get maybe a small sample of logs or logs that are not real-time. It takes a long time to make change of configuration. And once a content is stored in a cache, good luck try to invalidate it and purge it. So if you got some content you no longer want the customer to be served, you normally had to wait to the TTL to expire. Well, in Fastly, we actually architected the whole CDN to ensure that we got real-time visibility in their content. You can actually get all the logs real-time. You can stream logs to a number of endpoints. You can make instantaneous change in configuration to the global network in 5 seconds. And I think the most important thing is that you can invalidate content in the 150 milliseconds. And this is actually very important because you don't need to, this doesn't limit you to cache only static content. You can cache every dynamic content that you don't know when it will change in future. You don't need to worry about setting a TTL or having a content around stale and having somehow to withdraw it to purge it. You can just push the content, be cache it. When you don't want it to serve it anymore, you just purge it. And actually, this enables you to even cache APIs. We got customers that use our cache to cache APIs. So even if the API is changed, you just invalidate the results of the API. And I think it's very cool. Now, I would like to conclude with a couple of remarks regarding our commitment to open source project. So we love open source. We use our open source in our infrastructure. And we are very, very much committed to give back to the open source community. We give back to the community by contributing to projects. We commit regularly to large projects. We sponsor events like this one. Pizza is on us, by the way. And another thing that we do is we host free of charge open source projects on our infrastructure. So if you are maintainers of some open source projects and they want the open source projects being hosted by us, please come talk to me. We'll be very thrilled to have you on board to host your open source project for free. So that concludes briefly my presentation. Hope I didn't bore you too much. It wasn't too salesy for your taste. please excuse me if he was. And if I'll be around for the rest of the evening, I'll be easily recognizable due to my red jumper. Please come talk to me, come to say hi if you want to know more about Fastly, or if you just want to chat, please come to say hi. Now, I would like to give the word to Brett. Brett? Yeah. Okay.
Well, don't drink a beer and try and make steps. Thank you. Also, hint number 2, USB ports do not fit into HDMI slots. Ooh, that kind of worked. So, I'm Brett. I'm going to be talking about Vault and beyond secret storage. This is mainly because I think it's most of our way into Vault. We want to store secret data, we want people to be able to grab that, or certain people to be able to get that data. But Vault does so much more. And I'm going to talk about how we used Vault and the PKI backend to harden our infrastructure. So, once again, I'm Brett. I'm a DevOps consultant at OpenCredo. But one of my big passions is InfoSec. So, unfortunately, more on the red side than the blue side, even though this is more of a blue side talk. Yeah, it's people like me that get annoyed at Fastly for their WAF. But, well done. So in this talk today, I'm going to give you a brief overview of what is PKI, how we can achieve this with Vault, a very brief demo. I mean, I'm trying to cram this into 15 minutes. The issues we've encountered so far, and then conclusions where you can do further research from this. So what is PKI? We have to have, I mean, I'm following Armon. The only thing bigger than Armon is 80s hair. So this is Fleetwood Mac singing the wrong lyrics. If you know the song, the original title was Tell Me Lies, Tell Me Sweet Little Lies. And that's one of the things that PKI is designed to stop. So, other than Fleetwood Mac, who may have influenced PKI, I mean they definitely didn't, but this song, the original PKI specifications came out 1 year after this song. Coincidence? We also looked at other pop stars, Carly Rae Jepsen. And after her one big song, we have Jepsen. Jepsen is a tool developed by Affil, and it is a tool to, do you know what's really annoying? My notes aren't showing on this, but look, off the top of my head. So Jepsen is a tool to analyze services that cluster and are supposed to be distributed and fault tolerant. So definitely check out his blog. You'll probably be using tools that he's analyzed. I know Console got an honorable mention for taking the ECD tests and performing a little bit better. But in InfoSec, we have a big star. We have Taylor Swift. She's a little bit bleak, tiny bit. But she can also be funny. And then the developer told me, of course, our Oracle server is affected by Poodle. That's right there in the name. I mean, first of all, I'd like to start out that this has nothing to do with Big Red before I get sued. Poodle stands for padding Oracle on something, legacy, because I don't have my notes. I'm going to be few percent. We'll edit this out. That still didn't work. Okay, so padding Oracle on downgraded legacy encryption. And this was a really big SSL version 3 exploit. One that was so bad that an average 56 requests would get you 1 byte of encrypted data. Thankfully, we don't really use SSL version 3 anymore. So what is PKI, technically? PKI, a public key infrastructure, supports the distribution and identification of public encryption keys, enabling users and computers to both securely exchange data over networks, such as the internet, and verify the identity of the other party. So the main things to take from this is identification and securely exchange data. So what PKI is going to give you is a way to identify the computer service you're talking to is actually who they say they are. And then once that's established, you can send encrypted data. So in this talk, what we mean by PKI is the X509 specification. This will be the specification that most people see every day. Every time you go to a website that has HTTPS in front of it, that's an X509. Recently, or 2008, I believe, X509 version 3 was released, commonly known as PKIX, PKI Infrastructure X509. Nice and simple. So the way this works, and the way I'm going to show you in the demo, is initially you are presented a public certificate. With this certificate, someone is telling you, this is who I say I am. And so any information you send to them should only be able to be decrypted by their private key. But why, just due to that, should we trust them? I mean, I can create a self-signed set. It doesn't mean that Google Chrome is going to let me browse the site without a big red cross. And we do that through a security chain. So once again, referring to the demo, I'm going to show this certificate that was created is going to say, no, you definitely can trust me. This guy here has verified who I am. He signed the certificate. You should trust him. Once again, I can create an intermediate CA. I can create a root CA. That's no reason to trust. The intermediate CA says, no, you can definitely trust me. I've been verified and issued by a root CA. Now, the reason we trust root CAs is because they come bundled with our operating system. They come bundled with our browsers. If a root CA that's not trusted by a browser and not implicitly, or sorry, explicitly trusted by yourself, you're not going to get that green tick. So to demonstrate this more, I'm going to try and do a demo. This was hacked together last minute, so please don't judge me. So I'm going to try and go through this demo quite quickly. The final slide will have a link to the GitHub repo where you can grab this yourself, see what I did, see the scripts that are running, and just play with the PKI backend of Vault. I realize that you probably want me to make that text larger. Is that OK for everyone? Yeah. OK, cool. So I wasn't sure if I was going to have internet here, so I have done all of the grabbing of data beforehand. But the vagrant file, once again, is in the Git. It will pull down everything you need. So the first thing I'm going to do is spin up a Vault server. I'm going to do that in a Docker container, just because it's really easy. Pull it down, spin back up. And for some unknown reason, well, actually, it was known I was going to do more with this, but I didn't have time. It is living inside a lovely Docker container, Docker Compose. Yeah, so this is one of the reasons that I did that, but okay, sorry, a very, very quick change to my Docker Compose file. I downloaded it later, still once. Annoyingly, Vault latest and 0.6.2 are the same, but Docker is not gonna play ball with that. So we have our Docker server. I've done this in a way that you shouldn't normally. So this is actually spun up in dev mode. I've told it what the root key is going to use is. If you want some kind of security, don't do this. This is just for playing with. So the first thing I need to do is tell Vault to generate a CA. Now, Vault can do this one of two ways, really. You can either say, generate me a CA, this is the CA you will be using. But we try to keep our root CAs offline, just because if someone gets hold of your root certificate, someone on your team is going to be spending the next 10, 20 days trying to revoke and reissue every certificate that was that was given by that CA. So I was going to do this separate. Okay, so the first thing I'm going to do is create an offline root CA. This is going to be my master CA. Once it's created, the private key should be stored on a USB stick or something hidden away in a vault. It depends how far you want to go with security. Some people are really paranoid. Some people take their luck. So as a passphrase, I'm going to be really secure and enter the word password, because that has never been guessed. The rest of the fields I've given sane defaults for. The only thing I am going to change is the common name. So I set this vagrant box up with a host name of pki demo-info. So I'm going to call this ca.pki demo.info. So this has created my root CA and added it to my certificate chain. So just because you have a root CA doesn't mean it's going to be accepted. I mean, one of the main reasons for using Vault in this manner is because you're unable to get a certificate from another source. I mean, Let's Encrypt is amazing. If you can send an API request to Let's Encrypt, get an accepted certificate, it's great. Unfortunately, if you're running on your own machine for testing, or you're in a infrastructure behind a firewall and Let's Encrypt can't come back or connect back to you to authenticate you, it's not going to give you a certificate, which is great because you don't want to be generating certificates for google.com because they get kind of peed off. So now I have root CA certificate and it's now in my trust store. So the next thing to do is to ask Vault to generate me an intermediate CA signing request. And of course another foul. God. And it's going to be for the same reason. It's just here to annoy me. Mainly because BYOBU has not honored my bash.rc file. Never seen that before, but this can be corrected. So setup environment vaults. If I check now, I should have a vault address and somewhere a vault token. Yes, it's that. So let's run the same command again. No, not that same command. Still hates me. Situations like this. So you know how you plan everything right before. It's like anything that's going to need internet access, I'm going to get it. No. So what bit did it not? Ah. So the first thing it's moaning about is because in tests, I did not start up Vault at the beginning, which makes sense. No, fundamentally it's different. It's because I have not installed Vault on this machine. So we are going to go off-piste. Yay. And I am really sorry because just due to this, I'm going to eat into Armon's time. But I promise you, he does not have any Taylor Swift. So. Also, BYU is so what amazing person in the audience knows off the top of their head, the Docker command to grab something from within an image? I have a feeling it's Docker copy, but yeah, I'm going to grab it from the container. I can do that, but then the rest of my scripts aren't going to work. So I can. Sorry? So I want a volume copy. I will need to go into that container, grab the Vault binary out. CP? Thank you. Another OpenCredo person there. We're really good, apart from when we mess up. So, and now Armon's going to tell me where you're hiding the Vault binary within your Alpine image. Oh, on the spot. Oh, look at that genius. Spot on. He's good. this is why he's here. I mean, the downside now is going to be that Alpine uses a horrible thing that is not libc. But let's have a look. It works. Okay, so any things you compile outside of Alpine, don't run them inside compile. So now we have Vault. Let's get that to the place it should be. Ah, look at all those OKs. It's amazing. So what this is doing is it's creating the Vault PKI mount to say that this is an area where we're going to be generating PKI certificates. It's then tuning the Vault PKI mount to say that by default you can create certificates that last up to 10 years or 30 days. Tuning, configuring, and then finally it's given me an intermediate CA. So it's given me a certificate signing request. This is generally what issuing CAs do. They create a signing request for you after having verified you, and then pass that on to a real CA, something that can sign it. So in here you can see I have my Vault CSR. Now I need to get my CA certificate to sign that and generate a CRT. So once again, because remembering commands is not my strong point, we have another script. If you do, for any reason, despite this, this talk, pull this down, hopefully it will work better for you. So now it's going to ask for the passphrase, the passphrase that I gave when I created the CA. Password. So now we get presented with the details of the CSR. So Vault has asked for a certificate to be signed with a common name of vault.pkidemo.info. It's asked to have to be a CA. But it's also said to have a path length of 0. And what this does is say that you can create certificates, but you can't create certificates that can then create certificates. This is a leaf node. This is going to be the last part of our chain before our actual certificate. Sign it, commit it, go back to the last window, hit enter. Uploaded the signed CA, setting up role for server certificates, VPN server certificates, and VPN client certificates. So one of the many ways Vault implements security is within PKI, I'm setting up roles. And I'm saying certain roles can generate certain types of certificate. If I go to Vault list PKI, for this demo, we'll be using the PKI demo. So here are the rules that Vault will follow when any request to generate a certificate from this endpoint comes in. So I've told Vault that should anyone try to issue a CA against this role, don't allow any name, don't allow my base host name, don't allow bare domains, allow IP SANs, localhost subdomains. The main thing here is PKI-demo.info. So what I'm trying to say with this certificate is if you have an access key and you try to get a certificate from this role, you must say you're asking for a subdomain of pki-demo.info. And it can only be valid for 720 hours, which is 90 days. Another thing that kind of came out of let's encrypt. I mean, a lot of CA certificates, CA certs were giving you certificates for a year. But when it's this easy to create certificates, keep them small. That way you don't have the tedious task of maintaining a huge certificate revocation list. So now we have our role. Let's spin up a, no, that's not enough. Let's create some certificates. Once again, so this is just a small helper script. The first command is the role I want to use, and the second command is the certificate I want to generate. Yay, that's done a lot of stuff behind the scenes. Not actually that much. I should show you how easy it is to create these. All I've said is vault write format JSON, PKI issue, the PKI role, give it a common name, and say I want that in PEM format. What I've done then is use JQ to split that out. So I have a certificate file, a key file, and a PEM file. The reason for doing this is some servers want a certificate and a key. Others want everything bundled all in one in a PEM. They will take what they want. In the case of the web server I'm about to spin up, it doesn't care, but it was easier for me to create a PEM. So, fingers crossed. Yeah, of course not. Oh, sorry. Depending, I thought I wasn't going to have web access, so I half built this image. And the reason for that, so CA, I wanted to show you the generation of a root CA. So right now, this Docker image requires my root CA because I'm about to tell it to serve up some certificates. And if it doesn't have the root CA installed, it's just going to bork out. So this is my amazing CA certificate. Copy this into Vagrant demo. Just because one of these will work. Okay, despite that red warning, this has actually worked. Alpine has a slightly weird way of adding CA certificates to its chain. So it keeps them in the same directory as the CRT file that contains all of the root CAs. And then upon trying to add another CA, it moans that that certificate has more than one certificate in it. It's like, yeah, you generated it. You should be more than aware. So now we have that. Should be able to do. Second time's the charm. Woo! So now we have, this is using Caddy under the hood. And I really like Caddy because if you don't already have a CA, don't already have an SSL certificate, and you are hosting somewhere where Let's Encrypt could make a connection back to you, it will generate you a certificate on the fly and just plug that straight in. I am looking at trying to get that integrated with Vault because it's a handy thing to have on your local machine. So yeah, if anyone wants to help working on an open source project for that integration, we'd be very happy. So to show this has worked, which is, I mean, based on prior actions a risky move. Let's have a look. Yes. Welcome. If all has gone to plan, this file should be served over HTTPS. We can have a look up our stack. We can see, got the certificates, created an SSL connection using TLS version 1.2, picked a suitable cipher, and then to further check on this, one of my favorite tools is actually SSLIs. So many of you may have used tools like SSL Labs to check to see what kind of rating your site gets. That works really well if SSL Labs can connect to your machine, and also if you're running on the default port. If you try and, one of the things we had is we wanted to see how secure Vault was, but Vault runs on port 820. So if you ask SSL Labs to generate a profile for that, no. So SSLIs, CLI, runs the same kind of tests. It won't give you an overall grading, but SSL Labs provide the way they do their grading. It would be very easy to take all the information you get from here and give a grade. So the bits at the bottom look bad. That is not actually a failure. Here we can see it's connected to where we wanted it to connect. It's using TLS 1.2. It has a preferred cipher. And then other acceptable CIDRs. You can't guarantee everyone's machine is going to have every CIDR, every cipher that that your client supports. TLS1, cipher suites, all rejected. I mean, don't use TLS version 1 anymore. Compression, okay. One thing I've not kind of worked out, and I don't know if this is a caddy issue, is session resumption. No, sorry, that was a really stupid thing. The reason it doesn't support session IDs is because it uses TLS tickets, which is a much newer and much better method of maintaining sessions. Straight up, I mean, this is with no configuration whatsoever. Heartbleed, not vulnerable. OpenSSL, CCS injection, not vulnerable, even though that's actually a much newer exploit. SSL version 3 cyber suites, all rejected, which is great. Do not use SSL v3. I mean, now all of these failures down here are telling you about the main root CAs, the root CAs you'll have on your machines, the root CAs that have not signed this and have no idea of this. So here it's saying like Mozilla is going to say no, Apple is going to say no. But that's a good thing. This is not designed to be signing the certificates that you put on your public website. This is for infrastructure you control. And it's a good thing because microservices are really big at the moment. While you may secure the initial entry point, all too often you see microservices communicating between each other over HTTP. Now that means, people aren't going to break your SSL connection. But if they find another way into the machine, the first thing they're going to do is start TCP dump, whatever else. And if you're sending credentials information between your microservices, that's all plain text. That's really easy to find out. Further exploit, lateral movement. So this concludes the demo that kind of worked. we got to the endpoint I wanted to. So back to the very last couple of slides of the talk, I promise to be very quick. Issues. One of the issues, once again, Taylor Swift, every promise should come with a TTL because no promise is kept forever. Vault has done this for everything. And that is an issue we had and we are still kind of experiencing because we didn't think about this. In the demo, I've been using a root token. Now, a root token doesn't expire. That's your main thing. You should not be handing that out among other servers. That's for creating intermediate tokens, I guess. So the way this has affected us is we will create a certificate with one of our tokens, and our token has a TTL of 30 days. 29 days later, we're like, oh, this service should have a certificate. So we create a certificate that we say, well, this certificate should last 30 days. 2 days later, the token we use to create that certificate gets revoked. And then everything underneath it also gets revoked. So we have a certificate we expect it to be valid for 30 days, was valid till 2. It's a good security model. And it's one we should have thought of, but it may be a problem that you encounter when trying to use it. Another problem that was also listed here, but Vault fixed it just in time, just to ruin my talk, was it did not support, so it had extended key usage, but not key usage. And trying to write ACN1 blocks into Go to try and get a key out of it that you want. This was to do with VPN clients and servers. It's not nice. ACN1, don't leave alone. So, things to look at from here. Going to go through these really, really quickly. Content security policy, public key pins, strict transport security. These are all just to make HTTPS a little bit more secure. The only one I'm really going to get into here is strict transport security. Generally, if we have a HTTPS site, when someone comes to our site, I might be getting kicked off. When someone comes to our site, we issue a 301 saying, you can find this page at the HTTPS location. That's a great place for a hacker to come in. If you can intercept that first request, that unencrypted request, and send them somewhere else, or even just host that page for them, they still see www.google.com. It doesn't have the little lock, but some people don't look. And they're totally running on your server. Strict transport security stops that by saying, once a browser has seen this header, don't try and connect on port 80. It's not there. So the redirect happens at the client level rather than the server telling it it should go somewhere else. Can you see a theme? So one of the things to take away from this, think like say, Taylor Swift. She doesn't trust anything. Pay attention. I mean, there are ways around a lot of these things, but they leave little clues. If you're on a website with 4 wwws, then chances are someone's trying to get away from strict transport security and take you to a website that has never issued that header. Lastly, we are hiring, because I have to say that. We have a blog, and there is a GitHub for all of the code in this demo, which will be working by the time you get home, I promise. Thank you very much.
So maybe you got time for a quick question? Okay. So there's a bit of a change of a program because I was informed that pizza arrived, so maybe it's better to have a hot pizza rather than a cold one. So we can take a break for a pizza and come back for the next talk, and we can discuss more about your talk. Maybe there?
I'll just move over to someone else that knows more about it.
Okay. Thank you very much. Let's thank again our speaker.
Oh, thank you.
Should we jump in?
Yeah, sure.
Cool. Well, thanks. I'll try and make up for lost time.
Oh, no, then we'll take your time. You're the star of the evening, so take your time.
Go.
Okay.
Yeah. I'm ready to roll whenever you are. Oh.
Welcome back. Hope pizza was good. So we go on to the next talk. We got Armon. Everybody knows Armon. I don't think I need to introduce you. He's going to talk about Vault, how to secure our data center using Vault, and leave the stage to you.
Cool. Awesome. Well, thank you so much to Fastly for sponsoring and Sainsbury for hosting us. I'm gonna talk really fast to make sure we still have some time at the end for drinks. So please feel free to ask questions at the end if I sort of went over something too quickly. As super brief intro, my name is Armon. You'll find me all around the internet as also just Armon. And I'm one of the founders and CTO of Hashicorp. Because this is a Hashicorp Meetup, you probably are all relatively familiar with the toolchain. So we won't really dwell on what the other ones do. But today we're going to spend some time deep diving into Vault with cameo appearances by Console. Cool. So to set the stage a little bit, what are we actually talking about when we are discussing sort of the problem space Vault is solving? It really starts with sort of the broader secret management space. Does this have a weird echo, by the way? OK, cool. So if we're discussing secret management, the sort of first question that comes to mind is, what is a secret? What exactly are we actually managing here? And as we're talking about secrets, how do we delineate secret information from sort of merely sensitive information? So the best way to think about this is secret information is anything that can be used to authorize yourself, to elevate privilege, or to gain access to a system. So usernames and passwords, API credentials, TLS certificates, you're sort of elevating your set of sort of permission or identity or capability within a system. This is sort of distinct from sensitive information, which you don't want to lose, but can't actually gain access to things directly. So, for example, date of birth, email, these things are sort of sensitive, but you can't log into AWS with an email. So the kinds of things that we store inside of Vault are secret information. We don't store sensitive information per se, and we'll talk about how we manage sensitive information, but it's not stored directly in Vault. And the reason for this is the orders of magnitude we're talking about with each of these is very different. Your organization may have 1,000, 10,000, on the outside 100,000 pieces of secret information, but it's very conceivable to have order of billions for sensitive information. So the scale of management and how you sort of need to handle the scalability of the problem and the rate of access are sort of different. And so Vault's really more designed to live in that world and support you in this world without actually being able to store billions of records. But ultimately, Vault can be used to sort of directly or indirectly protect anything that would make the news if it got out. So sort of jumping in, Brett was really useful in sort of starting to lay out certificates as a very specific form of secrets. In general, they're sort of a pain in the ass. There's a lot of complexity around it. There's many levels of hierarchy. The tool chain is sort of archaic and involves black magic to get OpenSSL to do anything. And all of the documentation is completely abysmal. OK, so that's sort of the context as to what secrets are that we're trying to manage. What is the state of the world, or secret management kind of 1.0, as we like to talk about it? So when we're talking about kind of the state of the world, there's a few questions we need to answer, right? And these questions are, how are our applications getting their secrets? How are our human operators who need to interface with the databases and our applications and whatnot getting their secrets? How do these things get updated? So we change the root password of our database. How do we flow that out? How do we revoke it? Our root password ended up on an internet forum. OK, now what? What's the next step here? And lastly, how do we deal with our sensitive data? How are we encrypting data? How are we fetching it? How are we interacting with it? And this is sort of the most common scenario we see in the wild. We have a convenient file, our config.json, that we've checked into GitHub in plain text. And we've just gone ahead and put our MySQL username and password into it. This is super convenient because we just have to pull our application down, and there we go. We have our secret. If we need to update it, we just update our JSON file and git push. As you can imagine, this is sort of a completely abysmal story, right? Because what we're going to end up doing is pushing that thing into our Chef server or our Puppet server. And lo and behold, if we ask Chef for what this file is, we're going to get that thing back in plain text, right? And so is anyone else who happens to be able to talk to that thing or log into our GitHub. So why do we not want to do this? Why do we not want to use configuration management as our secret management tool? For one, there's generally very limited notions of what access control to these systems mean, right? It's not per user, it's not really group-based, it's not really app-based, it's sort of maybe all or nothing in the best case. Auditing tends to be very limited, so we don't really know which users had access to what credentials, which applications had access to them, which machines. There's a very limited ability to sort of introspect the surface area of access. Revocation, there's no real good story. How do we revoke something that Chef has now pushed out across the fleet? We don't even know really which machines have those secrets installed. And lastly, key rolling, there's no really great story there. So a lot of these problems stem from the fact that what we're doing is storing this information offline and distributing it out of band, right? So Chef and Puppet and whatever are sort of running out of band of our application. And as a result of this, we're not really in the data path to understand, did we access it, right? Like the secret was just on disk, did the app use it? Did a user SSH into that machine and read the secret from disk, right? Because it's totally out of band, we're not in the way to be able to interpose. So why not just move that secret into an online database, right? That way, the application has to request it, we're in the data path, the user can request it. If we need to do a key roll, we just simply change it in the database. Great, there's sort of a lot of problems to get solved if we move from an out-of-band distribution to an in-band. So why not use something that exists, right? We could use any RDBMS, Console, Zookeeper, whatever, pick your favorite online database. The challenge is none of these systems are really designed for secret management, right? And so there's a number of sort of shortcomings with all of them. They generally tend to have very limited access control. So most SQL systems, it's table level. So unless you want to do sort of a table per secret, it's really hard to go to very fine grain and say, my API server needs this set of credentials, my web server needs this other set of credentials in a fine-grained way. There's generally, very limited auditability or insight into what's been accessed. Maybe at best we know that a connection was formed with a given username and password or a table was accessed, but we really don't know at a row level what was being used. And lastly, usually most applications are talking to their database and the database is talking and storing on disk in plain text. So this is not really great. And so the state of the world tends to be, distributed, right? We have some set of secrets in Chef, some set of them in GitHub, some in our wiki, some in our Dropbox, and they're kind of everywhere. And the questions that become really hard to answer become, well, who actually has access to this inside the org? When were these secrets used, right? What is the attack surface? So as we're thinking about threat modeling and thinking about, what is the worst case, if we can't answer the other questions, it's really hard to understand what our attack surface is, right? And lastly, what do we do in the event of a compromise? If we don't know what the attack surface is and we don't really have an ability to reason about the access area, it's very hard to know, okay, this password ended up on the internet, now what? Certs are just a special case of this, right? In general, there's some Perl and shell scripts wrapping OpenSSL. Nobody really knows how it works. No one's touched it in years. And it's probably still generating like a 512-bit cert because no one knows how to change the configuration. So the state of the world when we look at kind of secret management 1.0 has some issues. In general, secrets are sprawled all over. There's really not a centrality of management. As a result, we have a decentralization of key management. It's really hard to understand who's been accessing it. Our visibility tends to be very limited. The certificate management is very painful. And if it's done at all, we generate 10-year-long certificates and just sort of like, OK, we don't want to cross that bridge until I don't work here anymore. And our break glass procedure is basically not defined, right? Like if we're compromised, it's sort of like, open up LinkedIn. So secret management 2.0, there's a lot of problems that exist, right? So we can only go up from here. And so this is where Vault comes in. Vault was sort of our attempt at saying, OK, there's a lot of known problems. How do we move away from that? How do we solve some of these challenges? And so we had a number of goals when designing and building Vault. One of these is centrality of management. How does it become the single source of truth, whether you're an application, whether you're a human operator? And so this really means different access patterns, right? Our applications are getting to these secrets in a programmatic way at very high scale, potentially. Our human operators are operating at a very different time scale, but they tend not to like memorizing APIs. So how do we make this sort of nicer for them? And then there's this sort of fundamental tension between practical security that is usable and sort of theoretical security that is NSA proof, right? And there's this sort of usability security trade-off that we have to sit on that spectrum. And so where Vault tries to sit is somewhere in the middle, right? practical enough that you're actually going to use this thing, secure enough that, short of, NSA being your threat, you're in pretty good shape, and doing it in a way that's modern data center friendly. And so what I mean by that is, designed to not rely on particular hardware. So if you're familiar with like HSM modules or dedicated security hardware, to not depend on those kind of things, to be able to run in sort of a pure software, elastic way. So these were its high-level goals. This got translated into a number of features the Vault has to be able to enable this. The simplest is just secure storage of secrets. So if I just have something that is sensitive and I want to dump it somewhere, how do I do that securely? It has a full certificate management toolchain. It has a feature called dynamic secrets that we'll dive into, and that causes us to bring in leasing and renewal. Auditing is deeply important to the system, as you might imagine. The ACL system is extremely rich, and it lets us go down to a very, very fine grain of access. And lastly, the system supports multiple authentication mechanisms, right? And the reason for this is the way our humans might want to log in with LDAP or Active Directory or GitHub is very different than the way an application is programmatically going to access the system. It's not going to do an LDAP login necessarily. So kind of rolling through these briefly, the simplest case is just secure secret storage, right? And the promise Vault makes here is data is always encrypted, whether it's in transit or whether it's at rest. Using sort of the highest standards of industry today, right? So this is 256-bit AES for anything at rest. Anything going over a wire is mandated to be TLS 1.2, so the highest possible protocol, just because then you avoid all of the downgrade attacks and poodles and heartbleeds and so on. So what does this actually look like in the simplest possible case? This is assuming we have a Vault that's running, and we just want to write a secret to it. So here we're using the CLI. It has sort of a hierarchical file system, so it's very POSIX-like in that way. So what we're doing here is doing a write against this hierarchical path, secret foo, and we're just going to set an arbitrary key value pair, in this case bar is equal to bacon. You might imagine this could be username equals foo, password equals blah, whatever sort of key pairs you wanted to store. And then at some point in the future, we can come around and do a read against the same path. So we do a Vault read against secret foo, and the key is that we get back what we wrote to it, which is bar is equal to bacon, and we get some of this lease information. And so I'll talk about what the leases are used for in a second here. I guess literally a second. So the next sort of a level up from the generic secret, which is just, I wrote bar is equal to bacon. When I do a read, I expect bar is equal to bacon back, is this notion of dynamic secrets. And the problem we're trying to tackle with dynamic secrets is, suppose what we had written was our MySQL username and password. So we actually just put in, user is equal to root, password is equal to whatever it happens to be. Now, we maybe have 50 or 100 or 1,000 web servers that are accessing this thing and saying, great, I need to get my MySQL password before I log in. The challenge is now all 1,000 of these web servers are using the exact same MySQL username and password. So if something is compromised and we see that MySQL username and password float around on the internet or get logged into a log file somewhere, or there's unauthorized access using that set of credentials, the question becomes, well, what's the point of compromise? Well, if 1,000 different clients had access to it, there's 1,000 possible points of compromise, right? All of a sudden, the surface you have to care about is huge. So wouldn't it be nice if there was some way to get away from this and say, I actually can uniquely identify the client, and as well, if I need to change my MySQL root password, I don't have to go and now revoke it from 1,000 different web servers. And this is sort of the idea behind dynamic secrets, is that can we add a layer of abstraction to shield us from this? So the way they work is we actually only provide the root password to Vault. So Vault will know the MySQL username and password for basically a root level access. And then what we do is we define a set of roles. This might be the production role, it might be a read-only role, it might be the DBA maintenance role. And each of these roles will have some subset of permission, right? So the production role maybe has access to do full CRUD operations on all the tables. The read-only role can only do reads for the purpose of replication, and our operator can just do maintenance commands. And so what Vault will do is when we ask it for one of these dynamic credentials, it will generate on demand a username and password that's based on that role. So we can go in and say, please give me a read-only role. Vault will go talk to MySQL, create a new username and password that are UUIDs and basically high entropy, hard to guess things that are specific to a particular client, and hand that back. And then now we actually have an audit trail that can tell us where we have a point of compromise. Because every client had a unique username and password, if we see that float around or end up in a log file, we know that web server 47 was the one that had that. Now, what happens if that client decides it wants to just use that username and password forever, right? Leases give us an enforceable mechanism to make sure that clients don't do bad things, like remember a username and password forever. And we'll talk about this in a second. So how does dynamic secrets sort of work? It's really not magical, so we'll sort of do a quick run through. So we might here enable Vault talking to the Postgres backend. Vault supports, there's sort of a list. There's a few dozen of these dynamic backends it supports. So we'll mount Postgres. Then we'll configure Vault and give it our root username and password for Postgres. In this case, just Hashicorp. Great. And we'll define a role. Here we're just going to name it the production role. We're not going to constrain this thing at all, so effectively it's still sort of root level. But we could have added a grant statement after this that provided only a specific set of privileges. And now what we're going to do is come along and read this production credential, right? So the path you can see is basically Postgres credentials production. What we're specifying is this is a dynamic Postgres credential, and the production role should be used, right? And so there might be read-only role and other type roles. And so what we're going to get back is this totally randomly generated username and password. And what happened here is we used the root Hashicorp user password to go in and issue a create user blah with password blah with permissions. And now what Vault is telling us is, by the way, this credential is only valid for the next 3,600 seconds. I've leased this to you for the next hour. This lease has a particular ID, and the lease is renewable. So now if we come back and do a read again, we get a totally different set of username and passwords with a different set of lease. So every one of our clients is going to have a different set of passwords. So this dynamic secrets is built on the fact that Vault has a number of pluggable backends. It's an extremely extensible system. The idea is, can we provide you a single API surface, a single set of policies that will let you manage kind of any of your database types, right? So you can generate dynamic AWS IAM credentials. So give your root AAM credentials to Vault and let it generate dynamic sub-credentials on demand. Cassandra, Consul, Mongo, sort of the list goes on. Some of the more interesting ones that we'll touch on the end if we have some time. PKI, we touched in a little bit of detail, but we can also generate one-time passwords for SSH. So we actually don't need to give developers our SSH credentials into production. We can let Vault be the only one that owns a key into any of our servers and let it generate one-time passwords. And that way we have an audit trail of who's SSH into what machine. So leases, we've seen these things crop up a few times. Fundamentally, anytime we do a read from Vault and it gives us a piece of secret information back, it's returning that with a lease. And the idea here is that if you imagine a username and password they're reading from a config file, there's sort of now an implicit contract that we've given our application saying, great, I started my web app, its MySQL username and password was whatever. This password is sort of assumed to be valid until the end of time, right? The web server is not going to stop using it at any point until it's restarted or reconfigured. So the assumption here from the perspective of the app is that I can use this password forever. So now what happens if I want to do a key roll every 30 days. I'd like to change the MySQL password or rotate an encryption key or change my SSL certificate. The problem is we have an implicit contract with all of our applications that the credentials they have are valid until the end of time. And so there's sort of a mismatch, right? As a security operator, I'd like to time-bound the sort of validity of these things, but our applications sort of make an assumption that's very hard to deal with. So what Vault does is takes the stance that every piece of secret information should have an explicit lease attached to it. So the application has to be aware, yes, this is your username and password, but it's only valid for the next X seconds, right? And then at the end of that, or periodically, this should be renewed or refreshed or regenerated. And now we can actually start reasoning about things like revocation, key rolling, and rotation. So if we have a dynamic secret, we can actually enforce this. Right? So what Vault will do is say, great, here's your dynamically generated username and password. It's valid for the next 3,600 seconds. If the application is misbehaving and decides it's going to violate that contract and it's going to use it forever, then Vault will just go and talk to Postgres and say, that's great, drop user. Right? It will just go underneath the app and revoke the credential. So this contract is actually enforceable by Vault. And this is possible because it still holds a root key and it's tracking all of this lease information. So it knows every single client what secret information it's sort of checked out and has on loan. And if it violates its lease contract, Vault is sort of free on its end to violate the contract as well. Now, that said, these secrets can be renewed. So an application that's well behaving might be checking in every 30 minutes and saying, great, I'm still talking to Postgres. I'd like to renew my lease. And Vault will come back and say, sounds great, I've extended your lease another hour. This is sort of similar to how DHCP works. Your machine comes up, it gets an IP, the DHCP server says, great, you have this IP for the next hour. Every 30 minutes you say, hey, I'm still on the network, I'd like to renew my IP. The challenge with DHCP is it's not enforceable, so if you decide to violate that, you get that really annoying pop-up that's like, another machine has the same IP, and it's just like things magically break. In Vault's case, things magically break, but only for the client. Secrets may also be revoked early by operators. So the sort of flip side to having these leases is, yes, Vault can use them to keep track of who has what, but this actually gives us a break glass procedure. So if we know, hey, our MySQL credential or our Postgres credential has been leaked, Vault knows every single client and every single MySQL credential that's been given out that's still currently active. So we can actually go to Vault and say, please revoke all of the MySQL credentials generated by the production path or the read-only path, whatever. And so we can start defining break glass procedures around compromises. And really the key for this is dynamic secrets make this enforceable, right? So in the case where I just wrote bar is equal to bacon, Vault has no semantic understanding of what that is. So if an application decides it's going to cache that forever, there's nothing Vault can do to sort of force the client to forget or revoke it. But in the cases where it understands the semantic, it's a Postgres credential, it's an AWS IAM token, it's a console token, because Vault knows what the type of that thing is, it can go talk to those underlying systems and revoke the token and make these contracts enforceable. Something you might sort of expect from a system like Vault is that it has a very flexible auditing system. So you can audit every single request and response that flows through the system. One of the things that's sort of key in the design of Vault is it's designed to prioritize safety over availability. And so what this means is it prefers to fail closed. So for example, if you've set up your audit log and you say, I want it to go both to my Splunk server as well as to syslog, if Vault for some reason is unable to log to any of its audit backends, right? For example, you have a malicious operator who's purposely disabling these things or blocking access so that an operation will not be audit logged, then Vault will simply fail the request. So it will fail in a closed way. If it cannot prove that it's been able to audit it, then it will just return an error to the client and refuse the operation. Everything that goes into these audit logs is also hashed one way, or it's HMAC'd actually. So you can search the audit logs by going and asking Vault, you know what, I suspect Armon has done something malicious. Please HMAC Armon and return what that is going to be. And then I can go search Splunk or search my syslog server and look at sort of what are the operations Armon has done. So Vault will maintain sort of the right keys necessary to search over our audit log, but without directly exposing secret information inside of it. The ACL system is also designed to be incredibly fine-grained. It's sort of looking at the kind of problems of an RDBMS and things like console is how do we get down to a very fine capability system so that you can be very nuanced in who has access to do what. So there's a role-based policy system. You can define sort of groups of policies that have sets of keys that they can access and update. Everything in the system defaults to deny. So it's designed to operate from a position of kind of need to know. What we've found in running large-scale systems like console is that it's much, much easier at scale to maintain a whitelist than it is to maintain a blacklist. So a sort of default allow policy is actually very difficult to secure at scale. It's very hard to reason about. And so Vault takes the stance that everything must be default deny, and you must be explicitly granted into knowing something. So what does sort of a policy look like? How fine-grained are we talking about? So Vault underneath the hood has a capability system that lets us delegate specific operations. And then we have a wildcard ability to sort of match sets of paths. So what we might do is say, in general, this policy allows an application to list or read anything that's stored under the secret folder in the system. For a particular secret foo, we're going to allow the application to both read it, but also update it, right? And so the update capability is actually distinct from the create capability. So you might actually have a situation in which you have a set of operators that you trust to update credentials, but you don't want them going through Vault and like adding new secrets to it, right? Willy-nilly sort of polluting its key value space. So we might give someone the update capability, but not the create capability, for example. And then lastly, there might be things that are just explicitly denied. So even though this is nested underneath the secret folder where we've granted read privilege, we're actually going to go to an even higher precedent policy and just say, the super secret thing, just deny that. So it's a very fine-grained system. It lets you sort of slice and dice to a very fine level who has access to do what. So then the question becomes, how do you actually log in against this thing? Like I said before, there's many different pluggable methods that Vault will support. Some of these are human-oriented, so things like GitHub, LDAP, user pass, designed for people interacting with the system. Others are much more oriented towards applications. So app role is something Vault does for sort of authenticating applications. It has a native EC2 integration, so you can depend on IAM roles and policies and AMIs and use that to authenticate. Mutual TLS, tokens, so on and so forth. And so there's sort of a split here between these. And the distinction Vault makes is you can have authentication plugins that are distinct from your authorization. So there's a single uniform set of policies that govern who has access to what. Those were the policies we saw before. But we can map that into many different authentication mechanisms. So we don't have to have one set of controls in LDAP and a second set of controls in GitHub and a third set of controls on top of mutual TLS. All of those can map into a consistent set of policy. A system like Vault is really designed to be an online database, right? The reason it's able to have audit logs and do all of this sort of interposition and online lease management is that it's an online database, right? It's running in a data center, and it's providing this information programmatically over an API. So as you might imagine, high availability is very important, right? If it's the system that hosts your database credentials and TLS and so on, it's sort of crippling to have this go offline inside your data center. So it has HA built in. If you run it on top of Zookeeper or Console or etcd, it will automatically elect a leader and do a failover in case the leader dies. So you can run as many instances as Vault will make you comfortable and let it automatically elect and fail over. The latest versions will even do request forwarding for you. So if you've used Console, it's very similar in the sense that you might have 5 different instances of Vault, and you're load balancing across them, but only one of them is the leader at any given time. Internally now, it will forward requests transparently to the correct leader. So the client doesn't really have to care about it. As long as the request gets to one of the Vault servers, it'll make sure it gets to sort of the correct leader in response. So one of the interesting challenges with Vault is if it's storing all of its data, encrypted in transit and encrypted at rest, then the question becomes, how does Vault access its own data, right? There's sort of a chicken and egg problem here. Right? So the data in Vault is designed to be encrypted at all times. And so when Vault starts, it has no real way of decrypting its own data. Right? So one answer would be, well, you can just put the encryption key inside of the config file for Vault, and it just reads it on startup. Then inevitably, that config file is provisioned by Chef. And so inevitably, that ends up in GitHub. And you've gone all the way back, and you basically just put the key to the kingdom back in GitHub. Right? So the stance Vault takes is it's going to make it just hard enough to automate this that you don't put it in Chef. And so it requires you to unseal the system online. So you bring up and start running Vault, and it starts in a sealed state. And once it's up and running, you provide it its encryption key online. So this way, unless you've really gone out of your way to defeat its security, you're not checking it in plain text. So what does this look like? We might start our Vault, and it says, we query Vault status, and it's going to say, I'm basically sealed. My encryption key has been split 10 ways. I need 7 of the 10 keys, so my threshold to unlock is 7 out of 10. And so far, 6 of the 7 keys have been provided. And so we'll come around, and we'll call Vault unseal, and we're going to put in one of these key parts. And then Vault will say, great, I'm no longer sealed. Basically, I've achieved my key threshold of having 7 of my unsealed keys, and now I've been able to re-achieve my encryption key, and I can read the data that's at rest. And so the reason, and we'll sort of unpack why there's multiple of these keys, the reason is, imagine you have all of this data that's encrypted at rest, right? And there's a single encryption key that's protecting all of this stuff. That master key becomes ultimately the key to the kingdom, right? And the operator who has it or the application that's in charge of it could fundamentally bypass any of the protections, any of the ACL system in Vault by just directly reading any of the cold data and decrypting it, right? Like, why bother go through a system that's going to deny you access if you can just decrypt the data in, cold? And so the challenge becomes, how do you protect against an insider attack, an operator who actually has this master key, the key to the kingdom, right? And so typically what you see is sort of like, the hunt for Red October is kind of the nuclear man controls, is you have a multi-man or a 2-man rule, right? Where multiple keys have to be inserted and flipped at the same time so that no one person can basically trigger the bad thing to happen. You need some sort of collusion. So the algorithm that enables this to happen is something called Shamir's secret sharing. And what it lets us do is actually decompose this master key into any number of pieces. So here we might be splitting it into n different shares, and we'll configure the system to say we need t of those n to recompute this key. And so the default here is when we initialize a vault, what it's going to do is generate 5 different shards of the key and require a quorum. So a majority of the key holders must be present to recombine to this master key. So when we first set up our vault, it generates the underlying encryption key that protects all of our data cold. That key is wrapped in this master key. The master key is then decomposed, and we throw away this master key. So fundamentally, there is no way to get back at what this encryption key is without having a majority of our key holders present. So what this lets us do is get around the one operator who has the master key and say, great, we have 5 people in the organization we trust, maybe the CEO, the CTO, VP of infrastructure, and the 2 InfoSec folks. And together, they have the ability to access the system. So in summary, the goal when we started was to look at solving the secret sprawl problem and really looking at 2 distinct categories of threats. One is external threats, so people should have no access to the system. And that's really protected through a crypto system. So making sure anything cold is encrypted, anything in transit is encrypted. There's, it's a reasonably high level of protection that, short of, nation state, you're going to be OK. The more real threat to most organizations, actually, is the internal threat, right? And that's protected by having a fine-grained ACL system and using the secret sharing technique so that nobody actually has the key to the kingdom. So Vault in practice, that's sort of Vault kind of in theory. How do we actually use this thing? What does it actually look like? Vault itself really is basically a database. It serves all of its commands over an HTTPS API. That's kind of a RESTful JSON interface. The CLI is just an API client around that. And so it makes it, the CLI more suited, obviously, for humans. The API designed to be friendly for programmatic access. But then there's a number of these other ways that people tend to access it. One of them is through console template, which we'll look at in a second. Another is if you're integrating natively with a scheduler, like Nomad, Kubernetes, Mesos, for example. And they might be interacting with Vault on your behalf. So the sort of primary, or I guess one of the ways in which we typically see an integration with Vault is in an application-aware way. So the application that's talking to Vault is aware of Vault. It's using an SDK. It's natively talking to it. And this requires that we're bringing in a native client library and directly communicating end-to-end. What's great about this approach is it means the secret has only ever been in memory. Right? The application is communicating over the network and using its secret in memory. Vault is keeping it in its memory, and we never touch disk anywhere. This is sort of the safest way to interact with Vault, but it's high touch. We actually had to modify our application. The simpler way of doing it is to say, you know what, I really don't want to modify my application in a high touch way. My app already knows how to read the YAML file or the JSON file, so can we just somehow get the secret into that thing and not have to talk to Vault? So this is a very common approach, and this is, people tend to use console template for this. It's sort of a horrible name for the tool. It started out only talking to console, and now can talk to all sorts of things. So what we might do here is actually say, I need my username and password to be templated in from Vault right before my application starts. So my application continues reading its file. It's unaware of Vault, and the interaction there is transparent. What's really nice about this approach is those sort of pesky leases that Vault has gets dealt with for us. So console template will automatically renew our lease. If the credential is rotated, it will re-render the template and reload our application. So the application can continue with its assumption that its secrets are basically valid forever. So what this might look like is we're defining, let's say, a YAML file that our Rails app is reading. And what we do is basically say, go ahead and materialize the secret from the Postgres credentials production path. And then we're going to just template that into the YAML file. So inject that as the username and password. So these are coming from the secret that we've read from Vault. We might be reading a different piece of configuration from console. So in this case, we might be reading out the size of our connection pool. And so we can sort of mix and match secret and non-secret information. So we've talked a little bit on how we handle secret information. How do we deal with our sensitive information, those pesky billions of rows? The most kind of common type of sensitive information that we see in the wild that people talk about is PII, right? So, and this information is everywhere. Social security numbers, credit cards, OAuth tokens when people sign on to our apps and they use like a Twitter login or a Facebook login, like that is a sensitive piece of information. tokens that we have for various services. We can even go further and say, do we consider a user's email to be PII? Do we consider their physical mailing address to be PII, right? And so as we start broadening the scope of what's sensitive, all of a sudden you realize a whole lot of stuff becomes in scope. And the questions we have to start answering is, well, what's the security of this storage, right? Are we just writing all of this stuff in plain text to Postgres? What's the scalability of it, right? If we're going to just ram it all into Vault, there's sort of a scalability challenge there. What's the auditability of accessing this information, right? So if it's all in plain text in Postgres and something gets leaked, how auditable is that? So a very common approach that we see with handling PII information with Vault is with sort of a special backend called transit. And what transit's designed to do is only interact with data in transit through Vault. So it doesn't actually store the data itself. What it does is it stores the underlying encryption keys and allows us to encrypt and decrypt data as it flows through Vault without forcing the storage problem onto Vault. So what it lets us do is avoid having secret management live in our end applications, like our web servers, our API servers, and it lets us build on top of the existing foundation Vault has around safely storing this, doing key rotation, yada yada, ensuring data encryption at rest and in transit. So what ends up happening is now we have a web server that has no encryption keys, but what it's doing is just flowing data that it wants to encrypt through Vault in transit and saying, please encrypt this and return the ciphertext back to me, and then storing that in a database. And when it needs to reuse that information, it flows the ciphertext back through Vault and says, please decrypt that and return the plain text back to me. So now if this data is going to be lost, we need a two-factor compromise. First, we need our data store, which has all of our ciphertext in it, to be compromised. This is sort of useless on its own, because you'd only be able to get access to the plain text by being inside the data center and being able to talk to Vault. And then you also need a compromise of Vault, right? And so this becomes now a huge hurdle to getting access to this PII information. It also allows us to decouple the storage concern, right? So maybe we have a scale-out store like DynamoDB or Cassandra or Riak or whatever that we're saying, great, we know how to safely manage billions of rows, and we can scale out the storage of this cold ciphertext data and manage that separately from the key management, encryption, access control, and auditing, which Vault can solve for us. And so Vault will then give us sort of for free key rolling and versioning and all of these nice things that we don't have to build into our apps. So briefly, what does this actually look like? You've probably, I guess this is now the second time we've seen, or maybe third time, Vault mount transit. So Vault has this, like I mentioned, this notion of dynamic backend. So before we mounted Postgres, and that gave us access to managing Postgres systems. In this case, we're going to mount transit. This is going to let us do key management operations. So what we might do is define a named encryption key. We're just going to call it foo. It doesn't really matter here. And what we can do is if we do a read of foo, we're going to see some information back. We're going to see basically the name of our key is foo. The underlying encryption mechanism Vault is going to use is AES-GCM. And this is not a derived key. I won't really get into the details there. And now to use this system, what we might do is call into it and say, please encrypt using key foo. So we're going to use the magic path transit encrypt foo. So we're referencing that same named key. And we're going to provide it some plain text. Here we're just going to pass in quick brown fox. And Vault will spit back out to us this random looking key, right? And so this thing is basically useless to anyone other than Vault. So what we can do is then flow that ciphertext back through Vault, now in a different path using Vault transit decrypt foo, so using the same named encryption key. And what we're going to get back is our plain text as we expect, right? And so now the properties, as we sort of think about this one layer deeper, is we have this in our audit log, so we know which client is doing the encrypt and decrypt, so we have auditability of the access. Our application never actually had the underlying encryption key, so we don't have to worry about, if our database got dumped, all of that data is secure unless we also believe Vault's internals were compromised. And because this named key is just a path, it's subject to the same ACL system as everything else in Vault. So you can imagine actually even going to the point where you say, great, my web server has the ability to encrypt data and write it to the database, but it doesn't actually even have the ACL permission to decrypt that data. Only my billing server has the ability then to make use of this foo key to do decryption. So you can go even further and make use of Vault's sort of ACL and capability system to restrict what operations are being done by either people in the system, applications in the system. So maybe we want human operators to be able to encrypt data but not decrypt, for example. So the nice things about the transit backend is we can sort of free ourselves from being concerned with our developers getting crypto right. There's a lot of nuance to it, and so we can sort of move that problem into Vault and say, are they using the RESTful interface correctly, which is a much kind of lower bar. There's rich libraries that can do this for us in many cases. So for example, there's a incredibly nice one for Rails that lets you basically tag a field in active record as encrypted, and it will automatically flow it to and from Vault to encrypt and decrypt the record transparently. So from a Rails perspective, you just sort of eyeball the field and say, yeah, this thing looks like it's sensitive. I'm just going to mark it as sensitive and not have to think about it anymore. Active record will automatically deal with it for you. And high performance can, if we start running into the limitations of Vault because we're flowing every single key through it, right? Every encrypt, decrypt. We've benchmarked it on reasonable hardware doing 30,000 ops a second, so it's a pretty high bar to have to hit. But if we get there, then Vault supports some additional mechanisms that allow us to scale this even further. And the final one we touched on a little bit is, can we start managing even more exotic types of things? So it's managing encryption keys with things like transit. It can manage dynamic secrets for things like Postgres and MySQL. And in the certificate authority case, it can actually be an internal certificate authority, right? So we can actually free ourselves from OpenSSL. So if we trust Vault enough to actually hold the root keys online, it can actually generate the root certificate authority. It can then generate the intermediates and sign leaf nodes automatically and do this in the same dynamic secret mechanism. So we could set up a role that allows our web server to generate a signed TLS certificate for www.hashicorp.com and have that expire every 24 hours, right? And now we don't really have to worry about, did we have our 10-year-long TLS certificate, accidentally exposed, right? We could even, there's really no reason you couldn't go down to 15 minutes and say every 15 minutes I'm just going to generate a new TLS certificate. And now I don't really care if it gets, leaked. The window of opportunity is very small. And most importantly, we can do this, without the tiers of traditional TLS. The sort of next level thing that this enables us to do is move to doing mutual TLS for our services. So as we increasingly go to a microservice architecture and we go from our monolith, which was just calling other functions in the same memory space, we didn't have to worry about possible network-based attacks because we're all in memory and have process isolation boundary. As we move to the network, that luxury goes away, right? There is no more process isolation. It's not just a function call. This data is flowing over the network. So we actually do have to care who is the identity of the person on the other side. Is it the service we expect to talk to? Is our data actually kept confidential as we're communicating? And so mutual TLS is sort of emerging as the industry de facto approach for solving this, right? The challenge with mutual TLS is how do you actually generate these TLS certificates and manage the PKI infrastructure, right? And so Vault gives us an answer for how we can do this. And what this enables us to do is move all of our services to using this and actually have end-to-end encryption within our data center. So we saw this a little bit briefly. You might mount it, go through, in this case, I'm going to just generate the internal certificate authority, the root CA inside of Vault itself. So we're just going to generate an internal CA. Great. I'm going to define a role. In this case, it's going to be only allowed to generate a key for example.com and some subdomains. So we might have api.example, test.example, whatever. And these are going to expire every 72 hours. So these are very short-lived SSL keys compared to what we usually see in the wild, which is years or decades. And then what we're going to do is just do basically a write against this. It's sort of a weird masking, but basically what that's going to do is cause Vault to generate a new dynamic certificate. So this is a new valid certificate. It's valid for the next 72 hours. It has a lease associated with it. So even if we do believe this thing has been compromised, and that 72-hour window is too long, we can still ask Vault to revoke this certificate, and it will automatically generate a certificate revocation list for us and manage the lifetime of the CRLs. So I beat myself to it. Yeah, so it can be revoked just like any other secret because it has a semantic. There is a revocation strategy for certificates. And what's nice about this is we never actually have to expose the private keys of our certificate authority. They can be held totally inside of Vault. And if we set up the permissions, by default, nobody will be able to access it other than Vault. And everything is sort of programmatically accessible through the ACLs in the same way. We have audit visibility. So it gives us sort of a consistent, uniform way of doing auditing, access control, and sort of management across this whole chain. And that's all I had. Thank you guys so much. One thing I will mention just super briefly is, one of our partner training companies, Forest Technologies, they've been sort of trained by Hashicorp and their curriculum blessed. They're doing a Vault training here on, not in London, not here, on the 20th and 21st. So if you're looking for more, sort of a multi-day deep dive into sort of how you actually use this, this one's coming up, and I'm sure they have other future ones on the schedule. But cool, and I think we have some time for questions before I stop gatekeeping the bar.
Okay, so a couple of trivial things. How quickly did you manage to copy my shell? I mean, ZSH is amazing, but that was mine. I got there fast. But the main question is, so I recognize you're not a charity. I mean, with your tools, you have easily saved my company tens of, maybe hundreds of thousands. But one of the things that came up during my my dry run today was Vault with HSM, which is currently a Vault Enterprise thing. Is there any plans to bring that to the open source version?
HSM will probably remain sort of an enterprise feature, but it might. I mean, I can't speak more than probably like a year out on our roadmap, and I think for the next year or so, it's probably going to remain in the enterprise.
And so one quick thing quickly. And currently, Vault is not pluggable, or you're not accepting pull requests for new secret managements. Is that going to change, or is there any way around that?
I mean, I think we probably pull in probably 3 or 4 kind of new backends from the community with every release. So PRs do get accepted at a pretty reasonable cadence. We are working on adding sort of a cryptographically secure plugin system. So what you will eventually be able to do is generate plugins that are just outside of the Vault binary and use code signing with it. So you can actually tell Vault anything that's signed by OpenCredo, I trust, or any plugin signed by Hashicorp, I trust. And then Vault can dynamically verify the authenticity of the plugin and load it in at runtime. So that will make it much more extensible so that you don't actually need to compile it in. I think the challenge, and the reason we don't use sort of Terraform and Packer's plugin system is the lack of sort of any cryptographically secure mechanism of verifying the plugin, which is fine for something like Terraform and Packer, but sort of frightening for something like Vault if it's all of a sudden just like linking in some random binary and providing secret information.
Yeah, so I mean, the thing at the moment is going through the docs, it says this is not going to be pluggable. What we want to do is concentrate on the core security. Although we have a really cool kind of use case that we want to use for it, which, in case anyone wants to know, is SSH CA signing or SSH key signing. So while you have a mechanism to generate one-time SSH keys, that works as long as you can connect to SSH.
Sure.
Whereas we want to say if an SSH key is signed by the
Sure.
authority, we can accept it. And so we will.
Yeah, why don't we take this one offline and let's just talk about it, because I think that is something that we'd be interested in potentially.
There was a question.
Yeah, I just wanted to check, when you're doing the Vault flow for the encryption, is it encrypting on the client machine, or is it actually passing it up to the cluster?
Sorry, to repeat the question. So when you're, just to make sure I understood, so when you're doing an operation against Vault, is it encrypting client side or encrypting server side? Did I understand that correctly? The encryption is server side. So TLS is used between the client and the server. So I guess, so one layer of encryption takes place when it's in transit from the client to the server over TLS, but then as it's going to cold storage, whether console or S3 or whatever the kind of cold store backend is, Vault is re-encrypting it under that encryption key that only it has. So the client isn't encrypting the data that's going to cold store, if that makes sense.
Okay, so you're not trusting the client to actually do the encryption in situ locally. But then
Correct, yeah, the client is sort of untrusted from Vault's perspective.
But then you're creating a bottleneck in terms of performance if you have to run it through the cluster for every client that's using it and on every request that needs to be encrypted.
Sure, yeah, so the question is basically, so we're creating a bottleneck for everything that has to flow through it. Yes, totally. Vault does have to, anything that it's writing to cold store, it's encrypting. Anything that it's pulling out of cold store, it's decrypting. In practice, that threshold happens to be like tens of thousands of requests per second on reasonable hardware. Like AES is really fast because Intel now has native instructions, so it's something like 2 gigs per second encrypt decrypt. So it's a really high volume of, in practice, the NIC is saturated far before your CPU is saturated.
Any more question?
Yeah, so if I want to run Vault and I want console as my HA backend, do you have any recommendations around how I can run my TLS certificates for console when I can't use Vault because of the chicken and egg sort of situation there?
Sure. So the question is, if we're using, so Vault makes use of a backing store. We recommend console for, maybe vendor bias reasons, but also just for battle hardened reasons. We just spend a lot more time testing it there. So the question is, if we're doing that configuration and we want to sort of TLS secure console itself, and we want to make use of Vault's ability to serve as our internal PKI, how do we sort of get around the chicken and egg problem that you need a running Vault cluster to generate the PKI certificates for console itself, but that Vault requires console to run? So in general, what we've seen is sort of a 1-2-step dance with it, which is you'll either bring up Vault onto a basically non-TLS secured console, set up the PKI backend, pull those out, and then restart console in its TLS enabled mode, or bring up Vault in basically like using the file system or in memory only, basically a non-console backend, temporarily configure PKI, and then migrate that data into console once it is PKI enabled, and then basically have Vault running on top of it. So you sort of have the Vault comes first, basically, is the answer to breaking the chicken and egg. So bring up Vault somewhere else, whether on disk or on an insecure console cluster, then bootstrap console, and then migrate onto it, basically.
Do we have any more questions? Yeah.
So at the moment, the PKI backend only supports CRL certificates. Is there any plans to enable OCSP or?
Yeah, so the question is, today we support CRLs, which is short for Certificate Revocation List. Those have been replaced with a slightly more complex mechanisms called OCSP. We've looked at it. It's substantially more complicated, and it's not as widely supported as CRLs are. So our view is basically, it's a lot more work on us to actually support this thing, because it changes, without getting sort of too into the weeds, it changes some of the internal details of how Vault would have to thread through request handling. And the surface of compatible clients that will actually handle OCSP is even smaller than CRLs. And CRLs are already basically a shit show for all practical purpose. So it's like, it was like, there was lower hanging fruit, basically, for the Vault devs.
Okay, this is going to be kind of cryptic, because I don't want to give away too much. But recently, someone posted on GitHub something that should have been through the responsible disclosure program. I really hope you already know about it.
That might be too cryptic for me. Unfortunately, I don't develop it daily.
Someone with some advanced memory forensics information could do some horrible things if they were on the Vault box.
Without being able to go into it in